Hi, everybody. Welcome back to Unit 11 of AP Physics C, Electricity and Magnetism. We're continuing our journey here in electric circuits. So in the last video, we talked about simple circuits. Now we're going to talk about what happens when they become compound direct current circuits. So everything that we talk about in AP Physics C, they're going to be direct current. Okay, and what that means is it's going to be like a battery source that's directly responsible for everything that's working in the circuit. Okay, so what happens is the elements that we talked about before, they can be connected in series and or parallel, right? So notice it says and or, because you can have a series circuit, a parallel circuit, or you can have a combination of those two, so the series and parallel circuits. The way you think about it is a series circuit is one in which the charge passing through the circuit must proceed or go through all the elements in that connection. There's no other path available, right? The way you think about this is like on a track, right? So all those runners on the track can only follow one path. There's nowhere else for them to deviate around, okay? What happens is, because of that, the current in each series circuit element will be the same. But, and you'll see in our chart here down to the bottom left here, so the current will be the same, but notice that the voltage, they're going to be different, right? The only time the voltage will be the same is if you have three identical resistors, okay? And then we also find what is called equivalent resistance. And for a series circuit, you're just going to add up all those all those resistances. Now, on the other hand, we have a parallel connection, and it's going to, essentially the current is going to have a chance to choose which way it wants to go. These are structured in a way that all the legs of the circuit are going to connect back to that initial source, that power source, okay? So, and you'll see here, I'll do this in a different color, but the voltage is going to be the same through each leg of the trip. The current is going to add up to the total current, so it's kind of the opposite from the series circuit. And then the equivalent resistance becomes this 1 over function or expression, okay? Now, there are benefits to both of them, all right? Now, the big problem with series circuits is the idea if one goes out, everything goes out. So each resistor essentially acts as a switch for that circuit. These are the old school Christmas tree lights, because if one went out, the whole strand went out. Now, on the other hand, parallel circuits are more effective because, now the series circuits have their benefits. It's a safety thing. Like if one went out, got overloaded, popped, then the whole circuit goes out, thus not straining the rest of everything there. Now, for a parallel circuit, this is the idea that if one goes out, everything else will stay on, right? This is kind of common in houses because if you don't want to turn, the lights to go off in the kitchen and all of a sudden the lights go off in the rest of the house, okay? And so you can remove the legs of the path, or the legs of the circuit, and everything else will stay on, okay? Now, we always assume ideal batteries and wires, okay? What that means is there's no internal resistance. So the wires and the batteries are not trying to use up the current like the resistors are. Now, if we don't, there will be certain situations in which the battery is not ideal, especially here in Physics C. And so if we need to figure out the internal resistance of the battery, or we need to figure out other things, the potential difference across the terminal is going to be the electromotive force minus IR, okay? And so the way this works out is that this is the internal EMF. This here is the internal resistance of the battery. Okay, I forgot the E. Now, we talked earlier in one of the videos, in the second video that had about simple circuits, we talked about ammeters and voltmeters. So ammeters are defined to measure current at specific points. They must be connected in series. It doesn't matter if it's a parallel circuit or a series circuit or a combo circuit. They have to be connected in series for them to work. Okay. Now voltmeters, I'm sorry, this should say used, not sued. Sorry, I just took a screenshot. So the voltmeters are used to measure the voltage across the 2 points in a circuit, and they must be connected in parallel. All right, so let's work on an example here. All right, so the figures below show parts of two circuits, each containing a battery of EMF epsilon and internal resistance R. Okay, so what happens is whatever voltage is here, right? That's what we call the terminal. And remember, the terminal voltage is a combination of the internal EMF and the IR from the resistance. The current in each battery is 1 amp, but the direction in one battery is opposite to that in the other. If the potential differences across the batteries terminals are 10 volts and 20 volts as shown, what are the epsilon and R for the battery? So essentially, it's gonna give you the same, E and R. But here's the thing: in electricity and magnetism, and specifically circuits, you're going to use a lot of the techniques that you learned when you learned systems of equations back in algebra. Okay, so we know our basic equation is going to be V equals epsilon minus IR. Okay, and so if we write it for the 10 volt scenario, okay, we would say 10 equals epsilon, what we're looking for, 1 amp, which is our current, times R. So we're going to call this the positive, right? And then we're going to go to the other side, and it tells us that one battery is opposite the other way. So our 20 volt, we're going to go minus 20, and everything's going to be the negative. Oh, we know that this is 1. We know the current is 1. Right? And so now we have a systems of equation, and I'm going to write one over the other, or write one under. I'm going to, oh, it's a weird looking epsilon. I know epsilon's a weird looking letter, but that was even weirder. And then what I'm going to do is I'm not going to add them, because if I add them, I'll get, negative 10 equals 0. So what I'm actually going to do is I'm going to subtract them, which here, for this part, flips all of these signs, okay? Sorry, I messed up over here. This should be a minus sign, which then turns this into a plus. I apologize. So that's always going to be minus on the right hand, the minus IR. And so this ends up being 30 equals 2 epsilon minus or plus 0, whatever you want to say. And so now we just simply divide both sides by 2, and it tells us that our internal resistance is going to be 15 ohms. Okay. Now we have our missing epsilon, and now we just substitute that in. So 10 equals 15 minus R, and then we kind of do a little algebra, plus R. So you get 10 plus R equals 15, minus 10, and you find that R is equal to 5. Hold on. Epsilon is not in ohms, epsilon is in volts. So this tells us that the battery has an internal value of 15 volts, right, or EMF of 15 volts, and an internal resistance of R of 5 ohms. If you want to double check it, you can use the negative 20, right? And we'd say plus 15, and we end up with negative 5 equals negative R, and there it is again. Right? And so again, two different ways, we found the same answer of 5 ohms. All right, in the next video, we're going to do a very important law, especially when we get into some of these compound and very complex looking circuits called Kirchhoff's rules.